for the invitation. It's a pleasure to be here, my first time in Brazil, and in this wonderful institution. It is quite remarkable, I thought, to kind of show it in the first slide. This is going to be a talk about a very new joint work with these three established and esteemed colleagues of mine who are all here. So we have Redmond, Berkeley, New York, and Cambridge meeting here in Rio. This is yeah, I don't see the chance of something like this happening in the upcoming years. So the topic is, the title is short, and that's because the topic is really, we're going to discuss something that is very basic, which is the classical random walk on the classical random graph. And we've seen various talks already in this conference discuss the cutoff phenomena for Markov chains. We'll see it again tomorrow morning. So I'll try to not spend too much time on definitions, and still, if you have questions, just feel free to barge in. Okay, so this is a theme that I heard a lot about from, I mean, it was, I actually became interested in it ever since I began my postdoc at Microsoft with Yuval, and that's the way that you can learn about very fine, delicate properties of the geometry by studying the random walk and the way it behaves as it explores the random graph, as it gets stuck in bottlenecks or in sparse cuts, as it tries to see vertices that are distant from it, from the origin, and so on. So the way that we're going to approach this topic in this talk, I'm going to compare two random graph models. Our new contribution is in this area. It's GNP, the classical binomial Erdős-Rényi random graph. And we're going to compare what happens here as given the known behavior that we've already established a couple of years ago on the random 3 regular or random regular graph in more generally, and its relatives. And we'll pay particular attention to the effect of choosing the starting position of the walk. Okay, so here's the Erdős-Rényi random graph. These are three pictures taken on an 1,000 vertex graph with the edge probability. So these are IID Bernoulli P variables for each of the n-choose 2 potential edges. Here we see the subcritical picture. So you see all the connected components are very small. They are logarithmic in size. At the supercritical point, which is just above 1 over n, you'll see one giant component. And all the rest of the, and in P, which is 1 over n, you see something where you have various components of intermediate size. And here's this quote. It's called, this jump from log to a power law behavior to linear is called, it was nicknamed the double jump in the original, one of the 2 original papers by Erdős and Rényi in 1960. Yeah, I realize now that the way that I phrase this quote, it's like the double jump, ... is one of the most striking facts concerning random graphs. So it could be, for instance, that the part that I omitted is something completely different in random graphs. So maybe it is the behavior, and the behavior of the random walk on it is one of the most striking facts concerning random graphs. Okay, in any case, this is saying what we saw in the last slide a little more formally. So we have this critical parameter P, which equals 1 over n. I'll denote by C1, the largest component of the graph. And we know that if P equals lambda over n and you take lambda to be less than 1, then the size of the largest component is log n. Okay, this is a, let's say, expected size. We can discuss things that are more refined. And this is just the order. If you take lambda to be bigger than 1, then you get a linear size component, this guy here. And if P equals not just 1 over n, but something that's called the critical window, which is 1 plus minus big O of n to the minus a third, okay, divided by n. That turns out to be the critical size of the window. Then the largest component will okay, here it's n to the 2/3 exactly at 1 over n, but the behavior, and we'll see something a little more correct in the next slide, the behavior carries throughout this critical window. The order of the largest component, of course, will, okay, it will stay the same, and as soon as epsilon will leave this n to the minus a third, actually we see it right now, as soon as epsilon has slightly larger order, then you see that the largest component starts picking up its size. So it was n to the 2/3 regardless of what epsilon was. Okay, at least there was a non-trivial distribution, and that was the mean. And then as you start increasing epsilon from n to the minus a third, then you get something that goes all the way from n to the 2/3 initially, all the way to n. Okay, so this is emerging as it emerges from the critical window. So here's another look at it. So just look at the first line. This is the size of the largest component, starting at n to the 2/3 at criticality. It's linear because here epsilon is fixed in the supercritical regime, and in between you interpolate between the two. Okay, just the usual interpolation. And what's more interesting in this slide, I think, is the behavior of the random walk on this largest component. Here it's not really, you can't really call it, I call it C1 and it's supposed to the giant, because here actually the second component is comparable in size. It's also n to the 2/3. As you emerge, there really is just one whose size is of order epsilon n as you exit the critical window, and that's referred to as the giant component. Yes? Yeah, so I guess so. Yeah, I mean, in general, for instance, when you're supercritical, everything outside of the giant is, of course, there's this reflection principle. So it would be. Yeah. Okay. We can. Okay. So let's look at the mixing time. Here, not only is the largest component of size n to the 2/3, what you should think about is, I don't know if you can make out anything from this picture here. These things look like trees. Okay, and there's a beautiful theory pioneered by Aldous many years ago, and actually new theorems and characterizations keep on coming on these Brownian trees. But if you just think of this as a random tree on n to the 2/3 vertices, then a random tree will look like, I guess one way to, one way to draw it would be, think of something like this, okay, where this is like n to the 1/3, and so is this, n to the 1/3. I don't know if it's if you see what I'm trying to calculate here. I'm trying to say that a random tree on n to the 2/3 vertices will have diameter which is n to the 1/3, typically, square root of the volume. Okay? Which means that the upper bound here, in this paper by Nachmias and Perez, is applied by just saying, well, of course, this is just a heuristical upper bound because this really isn't a random tree and you need to work, and they use beautiful martingale methods here. But suppose that this just was a random tree and this was its diameter, then you can just multiply the diameter by volume. That's a well-known bound on the mixing time, which I still didn't formally define, but carry with me. It's going to be in the next slide. So diameter times volume would then give you n. Okay? So that volume is n to the 2/3, average degree is constant, diameter is n to the 1/3, and it is tight in this situation. This area here of the supercritical regime, the fact that it's log squared n, is something that we'll see in a couple of slides. Okay, so you see the mixing time transitions as you move and increase p from the critical window to the strictly supercritical part. It drops from n to log squared n, and then there's an interpolation that we established in this paper with Jian Ding and Yuval in 2012. And when I said earlier that I got interested in this problem as soon as I started the postdoc, this was it took us several years to establish this result, but this was kind of like the beacon. This is what we were aiming at for several years. And the milestones were really milestones where we enhanced our understanding of the largest component. Okay, this is just a different way of writing it. If you write capital N as epsilon cubed n, and this actually will be useful fairly quickly, then you see that the mixing time is little n divided by capital N log squared of capital N. So there is this immediate interpolation between number of vertices and just log squared of the number of vertices. Okay. Any questions? Good. So here's the definition of the mixing time. I'll skip over this. This is just L1. Okay, we've seen this very, yes? We'll see, I'll show you a picture in a slide or two that will tell you exactly what's going on in the other regimes, But, okay, but you will see also what's the, yeah, okay. The volume, okay, the volume is everything, right? So it's in this strictly supercritical, so that's clearly overshooting, right? The volume is n, and you have log squared n. The diameter actually is log, but you're paying just another log instead of n. Okay, so this is the mixing time. It involves this parameter epsilon, much like in Yuval's talk, and the cutoff phenomena tells us something about the dependence on epsilon. It tells us that epsilon doesn't matter for the leading order term. That's all. Okay, so whichever two fixed epsilons you take, asymptotically, the mixing time will be the same. Okay, so keep in mind, there's always an implicit parameter. Yuval, in his slides, had a little n. I'm dropping this implicit system size everywhere just to make everything more friendly. But as the system size tends to infinity, we want to get the same asymptotics. And these are the two different pictures. It's known that, I mean, it's always monotone. It's known that it's okay. These things were described in detail, and Hubert already got Yuval to chew up on some of his talk for tomorrow, so I'm not going to describe any more, at least in that respect. I do want to say that even though cutoff was discovered many years ago already, so okay, nearly 3 decades after the discovery, so until 2010, I guess, we had one example of cutoff on a bounded degree graph. Okay, just one. This is this very nice paper of Yuval and Revel from 2004, and it is really non-trivial. It is the lamplighter on the two-dimensional torus, and it uses some delicate. I mean, the proof is hard. I mean, it uses some non-trivial estimates. You can. Yes, exactly. Okay, so a priori, it's unclear whether this phenomena actually is widespread as it was originally thought, or maybe it is something that is mostly associated with large degree graphs, or like works on permutation groups with many generators and so on. Okay, and these are the two canonical examples, the hypercube and the n cycle. I'm not going to say why there's no cutoff here and there is cutoff there, but I want to return our focus to the giant component in GNP. Okay, so what do we think? Is there going to be cutoff or not? So now I'll go back to your question about why we have the log squared n. So here's what the giant component looks like. If P is 2 over n, 3 over n, anything that's so the lambda here is going to be bigger than n fixed. We can forget from this point on from this point until the end of the talk, there will be nothing in this slightly interpolating regime between critical and supercritical. We are just supercritical. Okay, so lambda is 1.1. So what do we know about the giant? It looks like this. First of all, so now lambda is fixed. It's, let's say, 1.1. We take a random graph, and when I say a random graph with given degrees, I mean you look at, I give you a sequence of degrees. Here the degrees are themselves random variables, but given the sequence of degrees, I'm telling you draw a graph uniformly at random out of all graphs that have this degree distribution. So if you have n over 2 values of 3 and n over 2 values of 4, look at all the graphs where half the degrees are 3, half the degrees are 4, and choose one uniformly. That's what I mean. The degrees here are these truncated Poissons. and epsilon is something fixed that will go to 0 as lambda goes to infinity. So there is some degree sequence, and you take a random graph with that degree sequence. The take-home message from this first line is this truncation at 3. So minimum degree of 3, which means if you've worked in these locally tree-like geometries, it means that whenever you are exposing a ball around the vertex, you always have out degree 2. Like you expose a point, and you have 2 other guys to continue to. So it's expanding. This is very important. So this guy is an expander. We'll have a formal definition soon. It means that we like this guy, and we understand very well the behavior of random walk on it. We don't understand actually cutoff very well, but we understand a lot of features of random walk on it. Next step, you take this guy, you're not done with it, and you look at its edges, and you subdivide them, each one independently. You just had one edge, and now you're saying I'm replacing it by a path. So these new dark vertices spawn. Okay, these are new vertices, and each edge gets subdivided independently by a geometric. Okay, and now come the last bit. The last bit is that you take every point, both black and red, and hang an independent Poisson-Galton-Watson tree with a specific parameter. It's the same parameter for all of them, their IID. That's it. So you have a graph. And I have these funny names, kernel, 2-core, and giant. Well, giant is the big thing. 2-core is what's known as a graph. A 2-core in general is what happens if you successively eliminate leaves from a graph, which would mean that we are just eliminating all of these trees. And the thing that we had before the trees, remember, it was like every guy was on a path, or before that had degree 3. So there are no more leaves. This is exactly the 2-core, and this thing we started with, it's called kernel because of that's what it was traditionally called. Any questions? Okay, this is just, so this, I guess the biggest question that was unasked was, what do I mean when I say this approximately? It just means that formally it's one-way contiguity or absolute continuity. It means that everything that will hold on this guy will carry on and has probability 1 will carry on to the giant component with probability 1. So as the system size goes to infinity. What?
Probability going to 1.
Yeah, as the system size goes to infinity. Okay, so in other words, it means if you want to prove something on the giant component, try this guy first. If you get something that has probability 1 minus eta log of 1, then so does the giant. If you get something that has probability a third, you don't know. Maybe yes, maybe no. Okay, so that's what it means. Yeah. You sample the degrees according to this, and then you want a random graph, a uniform graph out of all those that have these degrees.
You can sample it using the conversion mode.
What was so maybe I didn't understand the question. What was the question? How to actually okay. Okay, so the way that this will actually be this will actually be useful later on. So what you do, you want to sample, let's say, a graph where half the degrees are 3 and half the degrees are 4. So what do? You write, so this is, you call this guy V1, and you write 3 copies for it. You call this guy V2. This guy, you say that he'll have 4 copies. You call it V3, and so on. Each guy has its number of half edges, okay? So this is one vertex. It's going to have 3 edges. This is another vertex. It's going to have 4 edges. This has 3, and so on. This is Vn. Has, let's say, 4. Okay? And now what you do is you just place a random perfect matching here, which means that every point here is connected to a random other point. Okay? Now, okay, like this, and maybe this guy goes like this, and this guy goes elsewhere, and now you collapse everything. So if there's an edge, then there's an edge. Here there were 2 edges between the vertices. That's also fine. You get a random multigraph because you can have multiple edges. You can actually even have a loop. But the number of loops and multiple edges is Poisson, which means that with positive probability you will have none. And if you had none, then this is the conditional distribution, given that there's none, is exactly the uniform one over all the simple graphs that have this degree distribution. And this is particularly useful because what you can do, you want to expose the neighborhood of a vertex, then you just say, well, one vertex is like these 3 half edges. I will expose who my neighbors are. And then I will expose who the neighbors of that set of neighbors are, and continue successively. If I discover an edge or a double edge or a self-loop, I terminate. Otherwise, I keep on going, and this is a dynamical way of exposing the graph while saying various things. So this paper that I mentioned by Yuval and Asaf Nachmias, they defined a martingale. They do this process, define a martingale, and that's how they control the size of it. Well, they show various things, control the largest component they have, but it's extremely useful. Anyway, this is for any fixed lambda larger than 1. Okay. We also have a result for lambda that tends to 0, but I'm not going to discuss it. Oddly enough, it is simpler to state when lambda tends to 1. Yeah. Okay. So we have this picture. How does this relate to the mixing time? Well, let's forget about the trees, cast them aside, and forget about these black dots that we entered. We started with this nice graph where all the degrees are 3. And this graph is an expander graph, which is something that we'll say something about soon. But this just means that the relaxation time of the simple random walk is order 1. Okay? Spectral gap is bounded away from 0. So it means that if you run the simple random walk on that graph, it will converge in time that is log of a pi mean up to a constant, and pi mean is n, so it will take you time log n to mix. So this was on the guy before we started dividing it. The problem is, even forgetting the trees, this subdivision is really deadly. It will kill the spectral gap, because and it will cause our graph to have paths. So remember that this was like a geometric. Let's think of these subdivisions as exponentials. Okay, so if you have something like n edges, order n edges, then you will have a path, according to these exponentials, of size log. And on this path, you will go back and forth. I'll start my random walk in the middle of this path, and it will take you time log squared just to exit it. And until then, you see a negligible part of the graph. So the mixing is at least log squared, and actually it's tight. Okay? And these 2 papers by Fontoullatakis and Reed, and independently Beniamini, Kozma, and Wormald, they show that this log squared n mixing is up to constants, the right one, in 2 very different methods. Okay? So this is why, okay? Good. So this answers your question from before. This is what's going on. You start at a bottleneck, you kind of jitter, and it takes you log squared n to escape it, and then you should be fine, but at least this dominates. You don't. And you could have, instead of starting from this kind of a bottleneck of a path, you could have also started at a heavy tree. Because Poisson, Galton, Watson trees, it is kind of like, it is the same kind of a trap. Again, you have this exponential decay of the effect of the trap, but you will have one that will have an effect of log. So it will take you log squared n to exit. Okay, so this actually is exactly what we want to ask. We know that if we start at a trap, then you take log squared n. So what happens if I just, but the traps are really rare, because you see these long paths. Okay, there's a constant number of guys that have log. And then as you shorten and shorten the paths, there may be more. But if I just looked at, I could kind of cast aside all those that are bigger than some threshold. Okay, log, 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 or something, and I will still have most of the vertices that are far away from these deadly traps. And the same for the trees. So most vertices are really far away from a bottleneck, and what happens if I start in one of them? So specifically what happens if I start from a uniform starting location in the giant? So this is the annealed mixing. I randomize my starting location. So an average over it, I want to understand whether I get, again, a bad behavior just as before, which would translate to saying, is it likely, even if I started in a place whose vicinity looked fine, is it likely to fall into one of those traps? Or do most starting locations look perfect and the network has very good essential mixing? So apart from this negligible part of the space, the network really is very fast to walk on. And this becomes really relevant. It's this topic of random walks on expanders. Because what are we saying? We say that we want to stay away from the traps and ask what happens if the walk starts away from them. So the first question then you need to ask yourselves in order to answer this is, what happened if there were no traps at all? So what's the behavior? Okay, so here we'll get, this is an example. We'll see this. This is a histogram of distances. We'll see it in a second. Everything is clear so far? We're just telling stories meanwhile. So still there is everything should be clear. So here's what an expander is. I already mentioned this means that the relaxation time is order 1. And in particular, it means that Yuval's product condition holds. Okay, relaxation time is order 1, but you need to spend time, log n at best, to kind of explore, this is bound degree graph, to explore a good chunk of the vertices. So you expect cutoff, probably. Okay? So in full generality, this thing is false. It took a while to actually, yeah, okay. You can engineer the counterexamples that we know that are known, and you can build an expander that violates this. But at least I think that the bulletproof way of saying it is that there ought to be cutoff when the product criterion holds and there is cutoff. Okay, so then, okay, but I guess in all the, probably, yeah, when Yuval was saying it to me many years ago, it was in all, he said, find me a natural example of a system that violates the product criterion. And then, okay, natural, it can be, again, natural can be loosely defined, but everything that is transitive, I got him to agree that would count as natural. And in our situations, we are kind of, if we are thinking about the random case, it is essentially transitive. Okay, now what happens for expanders? Why do we expect cutoff in a nice system that has expanders? This goes to something that Hubert will talk about tomorrow. You know, for expanders, that it can't be that just like a Brownian motion or simple random walk on the cycle before you rescale it, it's not that you approach stationarity as the walk mixes in time n squared, but if you want to get to within some epsilon of the stationarity, then you need the constant before the n squared to go to infinity as epsilon goes to 0. So it kind of stretches all the way, it sends mass to infinity. No, this isn't the case. So all the action happens between two constants, and this follows from the L2 properties. So this is actually given by the L2 bound given the gap, and this is just because of the diameter bound or bounded degrees. So everything happens in between two constants, so there shouldn't really be a problem. Okay, so let's in order to further understand it, let's talk about what happens in a random expander. So this is so you take in this model you take, just like we said, random graph with degree sequences, we can take a random graph with the degree sequences, which is all D, like 3 regular graphs. So a random graph uniformly chosen out of all of those with degree 3. And it's known that for any fixed D, this guy will be a very good expander. And what we see here on the right is an example for such a graph and the degree and the distance distribution from a fixed vertex. And what you can see is, first of all, this number is very small. So this is a graph on 1,000 vertices. But you see that around 10, essentially all the graph has distance 10 from this vertex. Well, 10, 11, there's a very small, so it's about log. And what you can expect is that if you walk from the graph and you kind of reach a distance from the origin that is roughly this popular distance, then since almost all vertices are that distance from that point, then you should have a good chance of seeing essentially every vertex with the right proportion. And then you should be mixed. So here's one testament for this behavior. This is so we count Yuval and me, okay? So this is author number 3, his involvement in 08. That was, I guess, in the PhD. Okay, so Nathaniel and Rick Duret have the following remarkable theorem. It's kind of like you start a random walk on a random 3-regular graph, and you fix a designated end point, C log 2n. So it turns out that the distance from the origin would be linear. Actually, I specifically didn't specify what the height of but it's actually, it should be skewed the other way around if this was really a one-to-one proportion between the x-axis and the y-axis. But you walk until your time becomes 3 log 2n, and at that point, it stabilizes and it stays asymptotically the same forever. Okay? So this kind of fits this picture here, because so the random walk walks. It kind of goes through vertices whose distance is small, and then it reaches the bulk, where essentially all vertices have the same distance from the origin, and it stays that way. So the natural conjecture is that actually at this specific location, the walk has mixed. Okay, and since every vertex roughly has the same distance from the origin, these two pictures would collide. One is this chart of the distance from the origin, and the other is the mixing time, is the total variation distance to stationarity that starts at 1 and goes to 0. And indeed, Duret conjectured the very same thing in his book. So the mixing time, this is the lazy, so there's a factor of 2, but it is the same thing. So saying that at that point, that is where the random walk mixes. Okay, and with Allen, okay, so now all of us have appeared in one context or the other. So with Allen, this was back when he was a summer intern at Microsoft many years ago. We verified these conjectures and showed that the simple random walk mixes exactly there, and the window is root log. You can get an explicit expression. We don't care about that for now. So 3 log 2n for the case of a random 3 irregular, and the window is root log. A non-backtracking random walk, actually, which does not go back on the same edge twice in a row, actually mixes faster. So this d over d minus 2 term is gone, and the window changes from root log n to order 1. Okay? Now, the reason that I'm bringing this up is actually this is very, very much. I mean, it seems for a second like, what does a random 3 regular graph have to do with GNP? Why should we really care about this very specific, neat situation where the degrees are such? But specifically, the reason that the simple random walk has this kind of a window, non-backtracking has this kind of a window, and non-backtracking is faster. Essentially, it follows. You'll see that the reasoning is very much related, and it is explained by this simplistic picture. It's a heuristics, and it's as follows. Instead of thinking about a random d-regular graph, which is probably a complicated object, you're just thinking about a d-regular tree. Okay? One that goes, so this is your origin of the walk, and the depth is log d minus 1 of n. So the tree ends when there are n vertices. Okay? And you start at the origin, and you will mix once you reach the bottom, because, and that much is clear. In this, it's unclear why this should give you the right, why this is a very good approximation of a random d-regular graph, but it's clear that on this model, by symmetry, as soon as you hit the leaves, you are on a uniform leaf, and the bulk of the mass, it has an exponential tail from the bottom. So once you hit the leaves, you're done. Okay, so how long does it take to reach the leaves? The height just does, in the simple random walk case, the height does a biased one-dimensional random walk, because you have D minus 1 guys pointing down and 1 guy pointing up. The non-backtracking random walk just goes down, zoom. It goes straight down. It is deterministic. So the non-backtracking random walk hits the bottom at time log base D minus 1 of n. Exactly. Okay, we're not thinking about rounding issues. The simple random walk has to fight the fluctuations of flip-flopping, going up and down until it goes down. So it has this speed, D minus 2 over D. Okay? So D minus 1 guy is pointing down and 1 guy is pointing out, so it's D minus 2 over D. So you pay a factor of D over D minus 2. Okay, now notice the window. The window from these fluctuations is root log because, right? Because you have log n steps, and each time, this is just central limit theorem, and each time you made the Bernoulli of whether you are walking here or there. And in the non-backtracking random walk, actually the variance is 0. But in the random cubic graph, it was order 1. But it is similar. At least you see the disparity. Now come the essential point. I want to rewrite this cutoff location like this. Okay? I will rewrite it as 1 over nu, and nu is the speed on the tree. Okay, for the walk. For the simple random walk, it's this D minus 2 over D. For non-backtracking walk is 1, because we just go down deterministically. Here I'm going to write 1 over log of D minus 1, okay, which is the branching number of this tree, okay, because every time, I don't want to define branching number. Let's say that this is the mean of if you had a Galton-Watson tree, then this would be the mean of your offspring distribution. These two things are the same, but the branching number is formally defined with flows. We don't want to do that. But it's like, but in any case, this number, I put this number here, log of D minus 1, log n. Okay? So the result on the giant is this. It is, look, it looks essentially the same. I have 1 over nu for the speed of random walk. Instead of on a D regular tree, it's now on a Poisson lambda Galton-Watson tree. So this is 1 over nu. I have something that looks like this 1 over log of D minus 1. And let's bear with me for a second. I'm not going to say what that something is. But this thing is actually, it is a beautiful, highly non-trivial fact that this thing is strictly less than, the inverse is strictly more than 1 over log of D minus 1. That this bold D is less than log of D minus 1. And here we have a log n, just as before, and square root n fluctuations. So the theorem looks essentially like the previous one did. Okay, so now what are the things? C1, of course, is the largest component of GNP, and we start at a random point, starting from a typical starting point. Nu is the speed of random walk on this tree. And D is the Hausdorff dimension of harmonic measure on this tree. Okay. So this is the main result. Which, by the way, I mean, we look, those of you who by now have forgotten what cutoff is, remember that just the first line was that cutoff is about the dependence in epsilon, that it does not matter for the first order term. So you see, there's no dependence of epsilon in the first order term. It just gets snuck into this root log n, essentially root log n window, which is correct. It is required essentially up to this little o term in the exponent. Okay, now what is this bold-faced D? So here's one way to define it. There are various ways to define it. But if you take a typical Galton-Watson tree, okay, so for almost every Galton-Watson tree, well, I want probably a non-degenerate. I will define this D to be the limit. There's no easy way of saying this thing. It is a complicated quantity. I'll just say it slowly. Okay, given a tree, a fixed tree. Okay, forget about Galton-Watson. If you look at a fixed tree, but it's infinite now, you can assign to each vertex a probability. And I want to, so you take a tree on which the simple random walk is, I expected to say this more quickly. But you take a tree on which it goes like this, it's infinite, and you want a tree on which the simple random walk is transient. That is essential. So given, by definition, since the simple random walk is transient on this tree, it means that there is a unique ray. This is denoted, this is the set of rays. So a ray is just a non-intersecting path that goes from the origin to infinity, on which the simple random walk will, such that the simple random walk will visit it infinitely often. And you would just say that the walk converges to this ray. Okay? So there is just a single ray that you will visit infinitely often. This is this limit, and you can just think of this ray as being the loop erased random walk, because you just erase all the loops, and then this thing just goes on forward, forward, forward to infinity. This is this notation here, loop erased random walk. Okay, so since you will choose one of these loop erased random walk traces for your walk to infinity, it's a random thing, I can define theta of x as the probability that x sits on this trace. It's the probability that x was traversed by the loop erased trace of the random walk. It's a theta of x. It is a flow because, okay, let's forget that I said that. So if this is just the probability that the loop erased random walk visits x, I can say that take now, this thing is constant given it is if you have a fixed infinite tree, these are deterministic quantities. Now I want to add a random guy, which is a real loop erased random walk. It may go on this ray, it may go on another ray. What this thing counts is just as you go with your loop erased random walk, you sum log of 1 over that weight for each point that you visit. Okay. Yeah, it is actually very intuitive once you read once you describe it in terms of conductances and so on. But this thing takes a little bit of getting used to. And you can write this thing as an integral with respect to effective conductances. Look at this creature here. The pioneering work of Lyons, Pimentel, and Yuval in '94 showed that actually, so there are various equivalent definitions of this thing, and you want to say that this thing is well defined for almost every Galton-Watson tree, and discuss in detail the probability distribution of the Galton-Watson as opposed to the random walk. What they showed, which is very surprising. Okay, I think it is. Were you surprised? It was many years ago.
We were surprised that we were able to prove it.
Okay. What this thing here says, M is the mean of as usual, it's the mean of your offspring distribution. What this means is, okay, this D actually counts very informally. It counts the probability that the loop erased random walk will visit a guy, right? I mean, if you take e to the minus that thing and forget about limits and expectations, it is essentially you want to understand the probability that the loop erased random walk will visit a guy. And if this was for instance a graph that was that was essentially the mean of the offspring distribution was 3, then in the nth level you have maybe 3 to the n guys, okay? And since the log is here, you would expect that if this D is essentially, well, there's the log scaling, you would expect it to have full dimension, so the entire branching number, if you cover the entire level at distance n equally, roughly equally. This result, what the striking result is telling us, is that as you are doing a Poisson-Galton-Watson tree, like this, okay? So this is the tree, and this is the entire tree. It tells you that there is a subset of, let's say, the nth level, such that this subset will contain the actual mass of the loop-erased random walk as it goes to infinity. And this subset will be exponentially small in this compared to this. Compared to the size of the graph at that point. Okay, this is what it tells you. Okay, and understanding. So there is this Hausdorff dimension. We cannot calculate it. Oh, okay, we can. There's an explicit form for it, but and you can try to approximate it. But understanding the measure that governs this integral is extremely complicated. This is a picture of the case where you have offspring distribution 1, 2, or 3 with equal probabilities, and there are like spikes, and in other situations there are holes. It's very complicated. So we don't really understand this quantity as much as we would like, I think. This picture is taken from the book Probability on Trees and Networks, which a small bird told me is going to be completed in like 2 weeks after, what, 15 years? 18. Okay. Okay, so I think that it would be instructive to discuss a simpler setting, which is just, instead of a Poisson lambda situation, instead of the actual random giant component of the random graph, let's just consider the situation where you have degrees, a random graph with degrees 3, 4, or 5 each on 1/3 of the vertices. Okay, that is a very simple example. Okay, I could have taken just 3 and 4, but I wanted you to feel like that when you are developing a ball around the vertex, it looks like it's 4 regular. So I took 3 and 5. And so you see, as you are looking at the number, you have a vertex, and you show me its neighbor. It's some guy, and I want to, okay, actually, one needs to do this a little carefully. But the actual attribute of this thing that you do not have because actually when you are revealing a guy, you are doing a size-biased sample, but let's ignore this for a moment. There are 2 key attributes that this model has that we do not have in GNP. We have here bounded degrees, that is very nice, but more importantly, the graph is an expander. Okay, just like we mentioned before, whenever you arrive at a point, you are guaranteed that you are going to at least split to 2 other guys. So every guy, until it's too late and you've revealed the linear number of guys, you constantly, you are just adding 2 more guys and adding 2 more guys. Okay, so here's a theorem. It looks like the previous theorem that we had, but the root log is actually now really a root log. There is no extra dirt in the exponent of the window. And what I want to emphasize is this little picture on the right here. If you remember that in the case of a random 3 regular graph by Nathaniel and Duret, and joining this with the result of with Alan Sly, so we knew that this is, let's say on a random 3 regular graph, this was the distance from the origin, and this was the mixing time. Like this, at the same location. What we have here, it's awfully close, is something that looks like this. This is where your distance to the origin stabilizes. There is some point. Again, you get the same phenomena. You walk from the origin, ... Almost all the vertices will have a typical distance from the origin. You will reach that distance, and then you will kind of stay in the bulk, where all vertices still have the same distance. However, the mixing time transition is actually way later. It is here. And it does have this cutoff. Okay? It occurs later, and the reason is this dimension reduction. It is the fact that as you are walking on the random tree and exposing your neighborhoods, there is a lot of guys that are unimportant. They are there, and if you are just interested in the growth of balls, then you would expose them, but you are not really interested in them because the loop erased random walk has a small probability of visiting them. And I think that, that understanding this phenomena for the non-backtracking random walk would be infinitely simpler. Okay? So remember that what does it mean to do a non-backtracking random walk? It means that you don't go to the vertex that you just visited twice. So you don't traverse the same edge in both directions twice in a row. Okay? So what does it mean? I'm now remember that when the graph was 3 regular, then the walk would the non-backtracking random walk would just go zoom straight down. Okay? And what was its speed? Its speed was 1. Okay? That much is still the same in this situation. What is different is that before we were uniform on the set of leaves, whereas now let's look at the non-backtracking random walk. If there's a guy here that has degree 4, then then we are going to visit each of its siblings with probability a quarter, as opposed to a guy that may have had probability 2 and gain more weight. Okay, so even though this is just a simple case of a non-backtracking random walk, and you don't have the loop erased, the loop erased is the path itself. There are no loops here to erase, and still you get a dimension reduction in the House law of dimension. What is speaking in the more general terms that we did before? There is a unique ray that you will go on to infinity. There's no erasing of loops. It's just your path. There is a unique path. There is, for every vertex, the probability that you visit this vertex. And if I show you the tree, then you will just look at guys that just accumulated on the way to those guys, you accumulated too many times the situation where the degree was big. So our case, it's 3, 4, or 5. So you had too many 5s along the way. And this decreased the probability of actually getting to this guy. Okay? As opposed to a guy where you had a lot of 3s, and this guy has a higher probability. So what you want is, you want to, first of all, wait until the time such that the important guys have a mass that is nearly n, and try to mix on them. Okay? And this happens way after the point where you actually see the entire graph, which is measured by this by the distance. Okay, that is the, so in some sense the visibility, not the point at which the speed. If you just look at the speed and you don't care about the House law of dimension. Okay, so yeah, so okay, so what do we do? I will say we don't have a lot of time, so and it is getting late, but I will say one line about what we do, okay, and then try to devote the remaining 5 minutes just to the challenges and what we need to do in the more general case. The rough idea of what we do is to say we are going to expose the neighborhood of a vertex, and now it looks like this. Okay, so we are exposing the neighborhood, the view, kind of exposing the graph as we go along. And we want to ignore guys that are just too rare, like this guy. So as we hit a branch and we say, oh, we hit too many, so this is just in the non-backtracking case. Let us not discuss, but at least in spirit it is similar for the loop erased. So if you see a guy who's as soon as the harmonic measure drops too much compared to what it should be, you stop developing that area of the tree. This kind of keeps you developing just the important bits, and so you can keep on going to the right point without kind of exhausting all of your vertices, if this makes any sense. Because remember, all these approximations are local. They break once you see the entire graph, of course, because you don't have a tree. You have a graph. But as long as you are kind of local, as you've exposed a sublinear number of vertices, you are still fine, and it still kind of looks like a tree. So it is imperative not to expose the stuff that you anyway aren't going to use, and kind of reserve that randomness for maintaining the exploration process. And then if you reach the point where there are, let's say, n to the 1 minus epsilon guys that are important, that are probable, that the simple random walk or non-backtracking random walk have a reasonable chance of visiting. What you want is to use concentration estimates to say that no guy here is too likely. Okay, so that no guy here, so you know that each of them has a good weight for the random walk, okay, for the loop erased or for non-backtracking. What you want is to say that all of that the probability, the maximal probability is, let's say, at most n to the epsilon times pi. Okay? So pi is like 1 over n. The stationary distribution, pi of v, is like 1 over n. And this is where it's important to understand not just the harmonic measure, but this quantity that we had before, but also properties like variance, the fluctuations. If every guy in this essential set has a weight that is no more than n to the epsilon compared to the stationary, then at this point, you say, I'm going to punt. I'm going to bound L1 by L2. Okay? The heaviest weight that I have is n to the epsilon. How long does it take me on an expander to kill a distance of n to the epsilon? Epsilon log n. And that is for any epsilon. Okay, so it is a trick. Yeah, and the idea is that you're not really trying to mix all the way. You're just trying to mix fairly well, and then let the L2 norm do the remaining job for you. Okay, so the problem is, of course, that this isn't an expander, the GNP. So that's a major problem, and it would completely destroy this argument. But there are ways to work around it, and this is one of those details that we don't have time for. So you need the right fluctuation estimates on this quantity, and this goes back to results of not just the first paper by Yuval and Robin and Russ, but this paper with Amir and Nina and Ofer from O2. So this gives us the right. We need the variance of this thing to be controlled for almost every Galton-Watson tree, and it follows from those ideas. And there are additional difficulties that one needs to sort out, like, for instance, approximating the walk on the graph by the walk on the tree, dealing with these trees that are just dead ends, and the entire thing that I was discussing was under the hypothesis that there are no leaves. You need to just be a little more careful when you add them. And then there are also extensions to graphs with given degrees, and the non-backtracking random walk specifically can be analyzed in those situations by a separate argument that gives the correct root log, even if you have degree 2 variables. Anyway, so 2 open problems to conclude. Open problem number 1 is a conjecture by Yuval. None of us is actively working on it. I'd be very, very interested in seeing, at long last, a resolution to either one of these questions. Yuval conjectures that every transitive expander has cutoff. This goes back to this question of what is natural, and the transitive is natural. But we don't have a single example, not even one. So random, explicit, build one, prove that one exists. Just find one that supports this conjecture that all of them are such. Or disprove the conjecture. But, okay, that's it. Thank you very much.